Morning, everyone. As our chair introduced, I'm happy to report on the radiative corrections for the MUSE experiment. I'll be very brief with the experiment itself. It was mentioned a few times during this workshop. I also don't want to discuss the theory of the radiative corrections themselves. That's not my expertise. What I would like to focus on is the connection of how to implement those corrections in the experimental analysis and what uncertainties we will have in the extraction of cross sections, not only because of uncertainties in the theoretical calculations, which hopefully will be maybe be clearer during this workshop, but also because we have finite knowledge about the experiment, and therefore the input to the theoretical calculations will be uncertain. So as briefly was discussed earlier during this workshop, MUSE is an experiment at PSI. The purpose of this experiment is manifold. It was originally motivated by the desire to measure precisely the proton radius, the charge radius of the proton. The experiment will measure several reactions. It will measure the elastic electron-proton scattering, and it will do that for positively and negatively charged particles. And it will do that for the muons, muon-proton scattering. So we have four different reaction channels, and they all require their radiative correction. So we need to have radiative corrections for positively charged particles, negatively charged leptons. We need to have radiative corrections which can certainly not ignore the mass of the lepton itself. Now, in the experiment, the aim is to extract the proton charge radius to study two photon exchange effects. We can do that because of the two charges of our leptons, and to directly compare electron and muon cross sections. As mentioned, the experiment was originally motivated by the proton radius puzzle. The graph here shows some recent results on that quantity. I want to just highlight that there are new experiments which have been performed after the puzzle came about. A lot of experiments support the extraction of a rather smaller proton radius. Other experiments are still in tension with those findings. There is a PRAD experiment, we heard about it, which gives a smaller radius. It's in tension with the early spectroscopy data, which are in tension with other spectroscopy data. So that's still an important subject where clarification is needed, and MUSE can play its role in that. We can directly compare proton radii extracted from electron and muon data. And the question about whether or not they are the same or different, that is a question we can actually answer much more precisely than the absolute value of the radius itself. But in the end, we hope to have 4 radius extractions from this experiment. The chart here was presented earlier too, so I don't have to describe it. Shown is here the electric form factor normalized as a function of Q square. You see in blue data from the PRAD experiment in tension with the MINDS data. And in the orange band below, you see the expected precision of the MUSE experiment. So you can see that we will be able to contribute to this discussion. The PRAD collaboration is planning on an update of the experiment, so there are more experiments hopefully to fill this chart. MUSE is not only about the proton radius, it's also allowing us to compare electrons and muon cross-section over a wider range of Q square. We aim for systematic uncertainties in this ratio quantity of about 0.5%. This is a very ambitious goal. Statistical uncertainties will be comparable. The way the data is plotted here is the cross-section ratio, electrons divided by muon cross-sections. The binning here is a bit unfortunate. You can imagine if there is no very strong Q-square dependence in this ratio, we certainly could bin data a little bit coarser, improving the statistical uncertainty. I don't want to go into details. It's a topic of Ron's talk, just following this one. But I mentioned earlier the two charges in the MUSE experiment allow us to study the two photon exchange effects. There, the systematic uncertainties will be rather small because a lot of experimental uncertainties do cancel in that ratio. And we are, in this case, statistics limited. Also here, the plot on the upper right shows the expected precision of the data from MUSE, and as a function of Q-square for that ratio. Also here, you can imagine that if you've been a little bit coarser, we certainly will be able to get a statistical precision which is comparable to maybe 1%. If you extract the cross sections and calculate the ratio, you're directly sensitive to photon exchange effects. I show in the lower right plots from Alexandra Tomalak. Just to give you a scale, expected effects are here of the order of 1%. The Q-square dependence is over a wider range, rather smooth and flat. So if we bin our data a little bit more aggressively, we may certainly be able to contribute to this discussion here. As you can see in this particular model, the expectation is that the two photon exchange effects for electrons and muons are different. Systematic uncertainties, as I mentioned, are certainly expected to be small due to cancellations. Now, MUSE is a little bit a special experiment. It's set up at the secondary beam line. So the incoming particle beam contains electrons, muons, and pions. So the experiment needs to deal with that. We not only need to measure the outgoing particles, we also need to track and identify the particles going into this experiment. And I just briefly show here a sketch of the experimental setup. The particle beam enters from the pi-1 beam line at PSI, goes through detector systems prior to reaching the target. That these systems include the beam photoscope to identify the particles, the gem detectors to track the incident particle trajectory. Then we do have a liquid hydrogen target, and scattered particles are recorded in the STT, our tracking device for the final state particles, and the plastic scintillators for timing and triggering. Further downstream, we do have a beam monitor to control reactions, particle identifications. It serves also for time of flight measurements. And after that, we do have a photon calorimeter. I'll come back to those devices. For the radiative corrections, this is my concept slide. We do measure in the experiment an integral of elastic and inelastic lepton scattering of the proton. Inelastic now in the sense that there may be photons involved, and we integrate in the experiment over those particle types. So once we have that cross-section measured, the experimental yield, we need to do corrections to find the Born cross-section. That's the quantity of interest to study our form factors. The connection between the Born cross-section and the measured cross-section, that is including the radiative corrections. Here I have a sketch shown in the center of the plot, which includes the emission of a initial state photon, hard photon in the forward direction. This is just one of the things which can happen. I just have that particular choice here for illustration. I mentioned that we do have trackers for the outgoing lepton, but we do also have a device which can detect photons in the forward direction. I'll come back to that later. At this point, we want to study the expected cross-section, and that includes knowing the Bremsstrahl cross-section from calculations we get from theoretical models. And it's a good point to acknowledge and thank you for the strong support we have from theory groups. I mentioned here a few. We have the ESEPP event generator. That is the one which I'm using for the rest of the talk. We do have the heavy baryon chiral perturbation theory from Fred Mir and his group. We have Elradjen from Andre and McMule from the PSI group, and we do appreciate their support. The ESCPP event generator includes the first-born approximation, first-order Bremsstrahlung processes, where real photons are a part of the particles which we can deal with in the final state in this particular event generator. And it includes virtual photon corrections, including two-photon exchange effects. So it is suitable for our study. It does not rely on the soft photon approximation. So we do have hard photons in the event generator. And it does not assume that the lepton is massless. I show here an example of an event distribution of a result from the ESCPP event generator at the MUSE kinematics. For most of what I'm showing here, I'm just choosing the central kinematic setting, 161 MeV over CB momentum, and a lepton scattering angle of about 60 degrees. There are two classes of events this event generator gives us. There is a class of events which are called elastic. These events do not have a real photon in the final state in the output of this event generator. This part is including, that's giving here the spike at 0. That's where the elastic scattering events are sitting. After a cut of about 1 MeV, if the electron were to lose more energy than 1 MeV, then real photons are included in the output. Everything between 0 and 1 MeV is integrated out. That's actually soft photon approximation, but only in this small range. After 1 MeV energy loss, real photons are being used in this approach, and that's what we call now inelastic. So we do have these two different types. Both types take fully into account first-order Bremsstrahlung. If I use this event generator and show for this particular case of the kinematic setting, the lepton momentum distribution in the final state, I get this result. In red is the result for electrons, in blue is the result for muons. We see on the far right the elastic peak. The elastic peak for the muons is a little bit shifted compared to the electrons because of the different recoil. And then we do see in red the radiative tail. You see that also for the muons, but for the muons, it's keep dropping over many orders of magnitude. For the electrons, it keeps dropping for a while, and then it starts rising again, before in the end, at 0 lepton momentum, in both cases, the cross-section drops down to 0. Now, the special situation with MUSE is that MUSE is not measuring the momentum of the outgoing lepton, as opposed to most typical scattering experiments with a magnetic spectrometer. So MUSE is integrating over the entire range of the lepton momentum, except certainly where we can't see the leptons anymore. And I will come back to that in a moment. So the integration range for the electrons will start around maybe 10, 15 MeV over C momentum, and we will integrate over everything up down to this point. And for the muons, the integration starts at about maybe say 80 MeV over C. For the muons, I'll mention that already now. It really doesn't matter too much because you see that the cross section is very low at that point, and it's just getting lower and lower. At threshold, where we start our integration, the cross section for the muons is about 200 times smaller than for the electrons already. So the muons are not so much of a concern. We mostly need to worry about the electrons because the cross section for low momentum or for outgoing leptons of the low momentum is already rising, and that's a concern for the experiment. I mentioned that the lepton momentum, if the lepton momentum of the outgoing lepton is approaching 0, the cross section drops down to 0. So we do have a maximum in the radiative tail, and Fred Mir's group has looked at that in detail. So I show here the two plots from their publication. You see on the left the result for the electrons. It's a double logarithmic plot, and you see the elastic peak on the far right, and then you see that the momentum distribution for the outgoing lepton does in fact have a local maximum. at about a few MeV over C. That's seen very clearly for the electrons. That's not there for the muons. The finding there was that if you change artificially the mass of the outgoing lepton, if you approach zero, there's a divergency. If you go to a finite electron momentum, there's a maximum. If you increase the mass further, that maximum at some point disappears. So that's just this effect we see here, but it is a concern to the experiment because the detection threshold for our outgoing leptons is at the point where this maximum is starting to rise very quickly. Now, where do the photons go? On the right here, I show a scatter plot where I plot the photon polar angle as a function of the photon energy. The elastic peak sits at 0, 0. These are the events which wouldn't have emitted any photons. You see that the photons go mostly everywhere, but predominantly they go in forward direction. This is the red island there at about 150 on the photon energy axis at 0 angle, and the photons go in the direction of the outgoing lepton. That's the stripe you see there halfway through the plot. If I include all the events which the event generator generates, I get back my red electron Bremsstrahl distribution. If I were to exclude the photons which go forward, I'm ending up with a green distribution, and you see that this is exactly what will help the experiment. Instead of integrating over range, starting at a point where the cross-section dramatically is changing, we now have a strong suppression of that effect if we were to exclude events where the photon was generated and went into the forward direction. These events appear there because if the electron lost already momentum because of initial state radiation, approaching the vertex, the electron energy is small and the cross-section is just higher. That is an effect which we see, and we need to ensure that we are not sensitive to this strong rise of the cross-section at low momentum. We do have an event generator. We do have particles in the final state. I just want to sketch here real quickly where they appear in the experiment. In the first of these 3 plots on the left-hand side, you see an event where in red you see the electron scattering at 60 degrees. That's the red line heading directly into the center of our detector. And in green, you see photons. These are secondary photons, or these are the photons from the event generator from the initial state radiation going forward. So we have a signal in the calorimeter, and we do have an electron going at 60 degrees and punching through our triggering detectors. This event would have been recorded. In the middle, you see a very similar event, except that the outgoing electron has very low momentum. We have a very high energy hard photon going forward. You see there's a lot of activity in the calorimeter. So we have a high momentum photon going forward. The electron has now little momentum and not enough momentum to punch through both of our triggering devices, the Sps detectors. So it gets stuck in the front plane, doesn't reach the back plane. This event would not have been recorded. So we do have this limitation. And in the third plot, I show a situation where we do have the scattered electron, reasonably high momentum. It punches through both of our Sps detectors, and we do have a photon generated in the direction of that electron. That event would have also been recorded. Now, from the few comments I made, it's clear that in our situation, I think in a more general situation, the radiative corrections will depend on the momentum of the lepton beam. It will depend on the scattering angle. It will depend on the momentum of the minimum lepton momentum we can detect or we choose to detect. We don't have a choice, but some experiments do have a choice. So that is what I call P prime min. And it will depend on what we do with the photons which are otherwise around. Most experiments just integrate over everything there. We have the possibility to select events according to the photon. And the detectors which are now involved in this selection of those parameters are briefly the incident lepton we can measure. I will come back to that in a moment. The scattered particle detectors determine the scattering angle in collaboration with the gem detectors, and not measure the particle momentum in the final state, but select a range of particles. I do have a change in my microphone. Maybe that is that a concern for the other people?
Should be okay.
Should be okay. Good.
Can hear you well.
Good. Thank you. Appreciate for that feedback.
Your video stopped. Can you turn the video back on?
My video stopped.
Why? The video of yourself for the remote people. I think it's wrong.
It's going. Oh, it's fine. Okay. Whatever you say.
Yeah.
So that was the scattered lepton side, and the photon calorimeter downstream is our device to give us information about the outgoing hard photon. The recall proton is also included in the event generator, but we can't make use of it. That proton will never make it out of our target. Let's go through those parameters which are included in as an input for our radiative corrections. The first one is the beam momentum. The beam momentum in MUSE will be determined we have an opportunity to determine that in very many ways. The first one is we set the channel to a certain momentum, and that's the precision instrument, and that gives us the momentum of the lepton. We can measure the time of light from the production target to the arrival of that particle to our detector system. That gives us time of flight measurement and therefore the momentum of the muons. And we can finally, that's the third option, that's the original plan. We can make dedicated time of flight measurements within our experimental system by measuring the flight time of pions and muons from the beam hodoscope to the beam monitor, and we can vary the flight path and get a selection of time of flight measurements, which we can then analyze and extract the particle momentum. And I would not say we have finalized the technique, but we have done preliminary work and convinced ourselves that we can measure the beam momentum to at least about a 0.2% precision that is within the requirements of this experiment. The scattering angle is determined by the gem detectors by Hampton University and the straw tube trackers from Hebrew University and Temple University. So that is for the incident lepton, that's going for the outgoing lepton. They collaborate and determine our reaction vertex and the scattering angle. The plot here shows a simulation of what's happening, assuming certain detector parameters. And the result is that we are strongly dominated by multiple scattering. So these detector devices, as they are designed, give us a precision tracking, but the experiment is limited by multiple scattering, and the reconstruction of the scattering angle for any given event is much better than 20 milliradians. It's not the scattering angle of an individual event which is critical now here for our corrections. It's actually the mean of those. And that is known to a much better precision if we have the sufficient statistics, which we do. And it's just limited by alignment and the setup of the experiment, and is expected to be better than 1 milliradian. The critical device in this discussion is the Sps detector. The Sps detector is the triggering device for this experiment, and it determines the lowest momentum we can see in the experiment. It's a fast scintillator, the University of South Carolina. We have reached time resolutions better than 50 picoseconds for the front wall detectors and better than 60 picoseconds for the rear wall detectors. Because the minimum particle detection threshold is such a critical quantity, we need to very well know the energy calibration of those detectors. Otherwise, we cannot compare with simulations. We also need to know that for ensuring a very efficient triggering system. We are calibrating these detectors with the thallium-208 gamma from room background, in fact. That is a very efficient method to do the calibration because these thallium-208 photons are abundant. We can measure all the detectors at the same time. But that's just one data point for calibration, and we wanted to ensure that we understand the response very well. So we did additional measurements with sodium-22 and yttrium-88 sources. So we have in total 5 Compton edges, which we use for our energy calibration in this example, and they are all consistent. So we are convinced that we do have a good energy calibration close to threshold where it counts. The plots on the right, I should have pointed that out. It's maybe not obvious. What we see here is the detector response for those photon sources, and we see the Compton edges of the gamma rays leaving their signature in the detector. We have 2 Compton edges for sodium, we have 2 Compton edges for yttrium, and we have this one Compton edge thallium-208 in the lower plot, but there's much more in the lower plot because it's just room background. There is just much more than thallium-208 there. We then shoot in the Monte Carlo simulation a broad range of electron momenta into our detector system, and we ask the question, what's the probability for that particle to be detected in the Sps detector? And you can see here that we do have a very high efficiency for high momentum electrons, but if the electron momentum is dropping too low, the particle cannot be detected anymore because the energy loss in the apparatus is just such that the particle may not make it all the way through to the last of our detectors. And we do have a threshold here at about 13 to 17 MeV/C in momentum. And you can see in the solid points, these are points which were simulated assuming a low discrimination threshold in the Sps detector. The open symbols show the situation for a higher discrimination threshold. The different colors correspond to different directions. And the only thing I want to point out, if the particle goes perpendicular straight through the wall, the threshold is a little bit lower because the material transversing is just thinner. If we go to the side with the lepton, then the amount of material is larger. So the threshold, the P prime min, that's the quantity we need to know for our radiative corrections, will depend on the detector settings for the discriminator, will depend on the direction of the particle. A more precise way of just glancing, compared to just glancing on the graph, is to determine the P prime min is to look at this equation up there. What we do in the experiment, we in fact measure the differential cross-section over the full momentum range, but that cross-section is weighted by the efficiency of seeing that momentum. And that quantity, the experimental cross-section, must be equal to what we would calculate theoretical if we just assume 100% efficient detector starting from the threshold P prime min. And if I use this equation, solve for P prime min, we get results very consistent with what we just would have guessed from the graph, about 14 MeV/C in momentum. But as in this relationship up there in the equation, you see that the cross-section enters, we do have slight modifications because the cross-section is changing as we pass over that discrimination threshold. So let me just make that side remark. The result of what the P prime min will be will also depend on what we decide to do with the photons, because of that weighting here with the cross section. For the muons, I just briefly pop that up here. The situation is very similar, except that the muon momentum threshold is much higher because the muon is losing much more energy in our detector system. If we just ask the question whether or not we would see an effect in the readout, whether or not we would trigger on the event, so ignoring the question whether or not we have actually seen a muon, the situation is much more complicated because now secondary particles from the decay of the muon will also be able to trigger the readout. But that is a situation below the range which are actually of any interest. So this is a curiosity which I just wanted to bring up here. Even if the muon would not even come out of the target, if it decays, we could still see the decay electron but that is something we can deal with in the experiment, and it has no relevance, in fact, for the discussion here. We can distinguish these events by time of flight measurements. Now let's go to the final point here, for the radiative corrections. That is the any information we can gather from the reaction vertex, giving us information about the outgoing photon. I have here on the left a sketch from the simulation of our photon calorimeter. It's a device made out of 64 lead glass crystals, 8 by 8. You see on the right-hand side 8 by 8 little tiny plots showing a detector response from a calibration run. Bin was leading the analysis on that. This device was commissioned just this year. It's an upgraded device related to the work which I present here. The decision was made. It is good to increase the angular acceptance of our photon calorimeter. We originally had a device which was using only half of the blocks, and I show that here in the light blue shaded range. It is really not so relevant here, but I just wanted to bring that up because we have from the older device a detailed analysis which I'm using now. And I just wanted to have that here for full disclosure. So also Win led the analysis of the test measurement, which we have done for the calorimeter. And what was done is we shot electrons of a very precisely known momentum into the device and looked at the detector response. That gives us calibration, and that gives us information about the resolution of the device. I need to know that resolution of the device for comparing with as an input for our simulations. We do believe that we know the momentum of the outgoing photon to better than 5 MeV/C. Shown here is the integral of the Bremsstrahl photon initial state Bremsstrahl distribution, and that distribution from our event generator is now folded with the resolution of the detector, which we know from the test measurements of our detector. So you see here in red the Bremsstrahl distribution for the photons. It's not falling off at 161 MeV because of detector resolution. This is what the experiment would see if we were to measure these photons. So that's shown in red. Now, once we have that on tape, we can select or veto on some of those photons, and that's what I'm showing here in green. We can select photons up to an energy of a certain amount and just veto on events which have more momentum. I want to stress here that we want to use this calorimeter as a photon veto, but we don't want to veto on all the photons. We only want to veto on the hard ones. And here I just chose 0.4 times the beam momentum as the cutoff energy. So we accept the events in green, and that's how it would look like if we just look at the front face of the detector. Without any interference, we will see a strongly forward peaked photon beam. And if we select only the photons up to an energy of 0.4 times the beam momentum, we see the picture on the right, where we do see photons on the front face of the detector, but these are only low momentum photons. With this input, I can go back to our Bremsstrahl distribution as a function of the lepton momentum, but now I turn it into a plot of the radiative correction itself. So that includes now an integral from P prime min all the way to the endpoint. And here I show the radiative corrections as a function of that value P prime min. And as mentioned before, the MUSE threshold sits at about 15 MeV/C. So if you go to the dashed line here, vertical dashed line where the MUSE threshold is indicated, the red point would give us maybe a radiative correction of about, say, 15%. That by itself is not the problem. The problem is that the red curve is very steep at that point. If you have any uncertainties about the position of that P prime min value, we do have a strong uncertainty in the radiative correction itself. If we were now to reject high momentum photons going forward, we are changing the cross-section, we are changing the radiative corrections. They get much more flat, and you can see with different choices of those cuts that we can impact the radiative corrections, and most importantly, the slope of the radiative corrections where it matters at the threshold of our device. Now, the question is which cut to choose. I said we don't want to exclude all the events. let me illustrate that here on the right of this slide. I show you plots which I've shown you before. So we see in the upper part the radiative correction as a function of P prime min, and in the lower part we see the photon distribution as a function of the photon momentum. Now, if I want to get the radiative corrections more and more shallow, which would be an improvement, in fact, I would need to cut more and more photons. The problem only is if I cut too many photons, you see that the photon distribution starts rising very quickly too in this logarithmic plot. So if I cut too low, I'm trading off the uncertainty in P prime min with the uncertainty of where my cut sits for the photons. So the question is, where is the best cut? And that is just naively just in the shallow region of this photon momentum distribution. I can very safely set a cut there without being much affected by my knowledge of the calorimeter. And I already reduced the uncertainty in delta in my radiative corrections by a whole lot, and that sits at about 0.4 times the d momentum. So that motivates my choice of 0.4 here. With that, it's very quick now because we know if everything's set, we can calculate the radiative corrections. I just want to briefly mention here the muons again. For the muons, all the discussion up to now really didn't play any role because the muons hardly radiate. The cross-section drops very quickly and is basically vanishing when it comes to the threshold. So the radiative corrections are small and completely independent of our detection threshold. I just wanted to mention that here for completeness. With that, I give a more detailed table for the results of our uncertainties of the radiative corrections. This table includes the kinematic settings of MUSE selected, and in the different rows, I show the parameters on which these radiative corrections depend on. And the only important parameters are P prime min, the momentum threshold for the outgoing lepton, and E gamma, which is the cut we make in our photon calorimeter. And the boxes here indicate those two rows. And I want to stress here, if you look at the numbers, they are important differences. The photon cut is completely independent of the angle. So it doesn't affect the extraction of the proton radius. So we do have different contributions, and there's one contribution which is not affecting the extraction of the radius. It affects the overall normalization of our cross-section. The red one is the critical one. That is a radiative correction which depends on the angle of the outgoing lepton, and that is a number which we want to minimize. Under the assumption which we discussed here, the correction, the uncertainty to the radiative correction due to our knowledge of P prime min, the uncertainty is less than 0.3%, and that is within the specs of the experiment. I mentioned last 2 minutes, I mentioned that we do have two different lepton charges. So we can look at the asymmetry of the cross sections between the positively and negatively charged electrons and muons. I plot here as a function of the energy loss of the outgoing lepton, the asymmetry, the calculated asymmetry between those two charges. This is differential. That's for every energy loss spin the difference. And what's interesting to see here that at the point of the elastic peak, you see it here for the electrons in red, the asymmetry is in fact a positive number. But in the radiative tail, it's a negative number. What we do measure in the experiment is the integral of that. And then maybe the next slide shows that more precisely. We do end up with a positive asymmetry for the radiative, for the cross sections. And the asymmetry will depend on our range of integration. And where MUSE sits, the asymmetry in these corrections is so small that we will not be able to see it. So that may be is a good news, because the radiative corrections here only include the soft photons. So whatever asymmetry we see is then most likely due to the more interesting hard photon contribution. If you compare electrons and muons here, you can see that the asymmetry decreases with P prime min, it decreases with the decrease in Q square, and the electrons in fact have a higher asymmetry the lighter particles. That's consistent with some of Andre's results. With that, I would like to quickly summarize. We do have in MUSE no magnetic spectrometer, so we're integrating lepton momenta over the entire momentum range where we can detect the particles. That impacts the extraction of radiative corrections. The angular dependent part of that is the important one for the extraction of the proton radius. And we believe we have the uncertainty under control to up to maybe 0.3%. That's not including theoretical uncertainties in the calculation itself. For the experiment, the most important part is that we understand the detection threshold for our scattered particle scintillator as well, and that we do have a good calibration of the photon count.